Hello, everybody. It's my pleasure to invite Professor Nicholas Sheffer-Barron from King's College London, who has the honor of giving the last SAC talk of this, I guess, British academic year, because we will resume, I think, in September or October. So the talk is on periods of elliptic surfaces.
Oh, thank you very much. Thank you very much, Jesus, for introducing me, and thank you to the organizers for inviting me. So indeed, I want to talk about elliptic surfaces. X of the complex numbers. So such an object is a surface with a morphism down to a curve whose generic fiber is of genus 1. And this is more or less the same as saying that the Kodaira dimension of X is equal to 1 in the classification of surfaces. So I'm going to assume, firstly, there is a section, sigma, which is fixed as part of the data. And secondly, that all singular fibers are reduced and irreducible with a single node. So 1 is a strong assumption. So the section will disappear under deformations, under a general deformation. But 2 is generic. It's stable under deformations. So let me say something about assumption 1. We can say a lot without assumption 1. Without 1. But the answer is, but the basic features are the same. But the basic features are the same. And the technicalities are easier. In any way, in fact, any X to C without a section has an associated Jacobian surface. So Jacobian means with a section. Which is the compactification, or birational to the relative automorphism group scheme. So I need to talk about, we can describe these surfaces in terms of the moduli space, or the moduli stack rather, of generalized elliptic curves. So I shall say that L bar is the stack of generalized elliptic curves. Concretely, this is proj in the orbifold sense of the grade ring generated by the 2 Eisenstein series of weights 4 and 6. So this is in the orbifold proj. And there's a picture which we can draw for this. So this looks like And then there's a so here's this. And otherwise, this is everywhere B of Z mod 2. And this has a geometric quotient, which is simply the compactified J line. And the degree of this map is 1/2. And here we have there are two distinguished points on the J line, and where J is equal to 0, and where J is equal to 1728. And the Picard group of the stack is because of its description as a proj is infinite cyclic, where M is equal to the line bundle of modular forms of weight 1, and its degree is 1/24. And what is M? M is the zero section, the conormal bundle, I should say. Zero section universal elliptic curve. And the tangent bundle, so small M tensor, 10 times. For example, we can give an abelian variety justification of this. Under the Kodaira-Spencer isomorphism, M tensor 2 times to omega 1 log infinity. So and infinity is the zero locus of Ramanujan's delta function, whose weight is 12. So the degree of the tangent bundle is 5/12. And it's important for what follows that this is positive. So under our assumptions, giving X to C is equivalent to giving a classifying morphism modulo left equivalence not modulo right equivalence. So the thing is that this, from our description, so what is the automorphism group of this stack? This stack has an automorphism group, which is GM, acting transitively on the complement of the locus with the J invariant is either 0 or 1728. So in particular, 0 is not distinguished. I emphasize this because I had It's slightly counterintuitive, but it is what goes on. And then if we define L's with the pullback of M, this is the co-normal bundle of the zero section, and its degree, well, a characteristic of X, which is, I'll write as H plus 1 minus Q, where H is the geometric genus of X, the number of two forms, and Q, which is the irregularity, is equal to the genus of the base curve. And I will define Z to be the ramification divisor. And then the degree of phi, by, for example, Riemann-Hurwitz, well, or by Noether's formula, is 24. H1 minus Q. So the degree of pullback of the tangent bundle is 10 into H1 plus 1 minus Q. So let's assume, I'm sitting at throughout this talk, I'm going to assume that 10H is at least 12 into Q minus 1. So this has the effect of then the stack of Jacobian elliptic surfaces, JE of Jacobian elliptic surfaces, is smooth of the correct dimension. Its dimension is the degree of this ramification divisor, which is 10H plus 8 into 1 minus Q, which I will call N. And then by looking at the ramification, well, in fact, that we have a short exact sequence. These are of sheaves on the curve. So this co-kernel is the tangent space to the stack at the point X. So this tangent bundle, tangent space, excuse me, naturally a sum of lines is naturally a line bundle. On Z. Now, our assumptions on Z, well, let me, okay. And I want to bring in the, before I bring in the cohomology, let me remind you what the geometry of what this stack looks like. So I have the stack of surfaces. I can go down to the stack of pairs consisting of a curve and a line bundle, and then I go down to the stack of curves, just the moduli stack of genus Q curves. So this fiber is abelian of dimension equals to Q, and this fiber here, the fiber is P of H0 to 4L, direct sum, 6L. And if you, so there's the moduli space of curves at the bottom, there's an abelian fiber, and then there's a projective space fiber, which comes from looking at the Weierstrass equation. So I want to bring in the cohomology of the surface. So we'll define the primitive cohomology to be the part which is orthogonal to the section and the fiber. And then, so this has a Hodge decomposition or Hodge filtration, which is better for our purposes. So then the primitive part, the dimension of this primitive cohomology, is equal to the same number n as before, just by calculation. So this appears as a something of a coincidence, but it's a coincidence which we can exploit rather than explain. So let me just draw in the Hodge filtration. So I've got 0. So this piece is just of dimension h. This piece is of dimension n. And this piece is of dimension h again. And at the bottom, of course, we have the space of holomorphic two forms. At the top, we have the dual of the space of holomorphic two forms. And in the middle, well, we have H11. And what I want to remind you of next is that there is a relationship between cohomology and forms of the second kind. So suppose X is any smooth surface surface. First, that D in X is a smooth curve, and eta is a meromorphic two form on X. With poles of some order along D. I'm going to assume that n is greater than equal to 0. Then there is a residue which is a class in H1 of the curve with coefficients in the complexes, and it's defined as follows. If gamma is an integral cycle on D, then there is an S1 bundle, let's say capital gamma, mapping onto gamma. So gamma is in the boundary of a tubular neighborhood of D in X. And the residue of this class, of this form, or paired against gamma, is just the integral, 1 over 2 pi I, sorry, times the integral around gamma, the two-cycle gamma of the two-form eta. So this makes complete sense because eta has poles along D, but gamma is disjoint from D, so this integral makes complete sense. And then eta is of the second kind. If this residue is equal to 0. And then this is the obstruction, and then eta represents a class in H2 of X, the complex coefficients. In other words, you can think of the residue as being, eta, of course, represents a class in the cohomology of X minus D, and the residue is the obstruction to lifting the class in the cohomology of the open surface to a class in the cohomology of the whole of X. And if you can compare this with curves. Suppose I have a complex curve, Riemann surface. Then the space of one forms represents or defines first half of the cohomology of C, and forms of the second kind here, which is represent all of the cohomology. So for curves, of course, being of the second kind simply means that all residues vanish, and the definition that I gave for differentials of the second kind for surfaces works, or indeed is a generalization of the same thing for one forms on a curve. So, also this description, so this is an additive description of the cohomology. This is also, this description is also multiplicative. If you have two forms of the second kind on C, then we can compute the cut product of the cohomology in terms of an expansion of, in terms of expansions around the poles. So this is 1 over 2 pi I times the summation over P being in the polar locus of eta, API, AP, right. I see something's gone wrong with my notes. Right, so API, AQ, B, P, J, I have to sum of I plus J equals to minus 2, minus the sum over the poles of omega, I plus J equals minus 2, whoops, of a similar thing, but where we have a QI, BQJ, where omega has an expansion in terms of a coordinate at each point. ZP to the I, DZP, eta summation B, PI, CPI, DZP at any point. So at each point, you choose a coordinate, and then you can compute this, the cut product of these classes by an explicit formula. And this is simply a general, the proof of this is, I mean, it's in the textbooks. It's it's the generalized form of the Riemann bilinear relations, but to generalize to allow the forms to have poles, but assuming, of course, that they have zero residues. Notice, just as a piece of algebra, that this is not, of course, equal to the what you get by wedging these two forms together, because of course the wedge product is 0. So for surfaces, I don't know of a general such multiplicative description. In higher dimensions, we lack in general that's the crucial word there. Any form, a means of calculating even for surfaces. So when I say for surfaces, it's probably better to say that. But for elliptic surfaces, we can do something. So let me just let E sub P denote the fiber over the point P. So this is a curve in X. Then, like the theorem of Cox and Zucker, for all A in this ramification divisor, so remember that this capital Z is the ramification divisor of the classifying morphism, there exists a meromorphic 2 form of the second kind, and I've forgotten double poles along E. I'm going to put in an assumption here, which I should have put in before. I'm going to assume from now on that Z is reduced and disjoint from the locus where J is equal to infinity. In fact, the ramification divisor being disjoint from the locus where J is infinity is equivalent to our assumption that all the singular fibers were as simple as possible. Right. Of the second kind, such that, well, and rather, this collection of 2 forms of the second kind is a basis of H11 of X of the primitive. So let me explain why these forms exist. Because it's important that we have a point in the ramification divisor. So the reason is this: the reason for the existence of these eters is that locally on C there exists an involution of X, iota of X, such that iota upper star of Z is equal to minus Z, and iota upper star of W equals minus W, where Z is a coordinate on C and W is a fiber coordinate. And so anything of this then is the sum over to 1 B sub n like this. So my point is that what I've just written down is an expansion of any two-form with double poles along the fiber, which is invariant under iota. But then, so iota upper star of eta is equal to eta, while iota acts as -1 on the cohomology of the fiber. So the residue must be 0. So what this proves is that these etas define cohomology classes on X, but it is not clear a priori that they live in the H11. So what I want to do, what I really want to explain to you today, the first thing I want to tell you about is a proof that in fact, these etas are orthogonal. So, and this is part of a variational approach. So theorem, let me go to the next page. Theorem. For every point in Z, there's a one-parameter variation this will be a threefold mapping onto a convex disk with parameter t of X, such that the derivative of the period map so what's the derivative of the period map? It's going to take the bottom piece of the Hodge filtration to the quotient to the next graded piece. So remember, this is H dimensional. This is N dimensional. Has these properties. One. Its rank is 1. I'm assuming that I'm assuming here that there are some forms to differentiate. Its kernel is the space of two forms that vanish along the fiber minus and this we can, I should say at this point, the bundle of two forms on X, because the surface is elliptic and has a section, the bundle of two forms on X pulls back from a line bundle on the base curve. So I can identify this with Kc plus L minus the point A. And thirdly, its image is the line generated by this form is generated by the class of eta A. So in particular, so indeed, eta A is in H11. And fourthly, for all points B not equal to A in Z, the derivative of the class eta B is a linear combination eta A and eta B. So given all of this, let me, the proof of orthogonality so goes as follows. Right, so I compare, this intersection pairing is 0. So now I'm switching notation. This is the cut product of the class of these two forms. So this is certainly 0 because omega is in the bottom piece of the Hodge filtration and eta B is in the next step up. So these two are always orthogonal. So I can differentiate this. Of course, by the Leibniz rule, this is simply d by dt of omega eta B plus omega paired with the B. So what is this? This is simply eta A, well, up to scalars, this is eta A and eta B paired together, plus this pairing here by part 4. But again, this is equal to 0. So orthogonality is proved. The reason I emphasize this is that we don't have a formula in general for computing these cut products, even though we can write down the forms. So everything depends. So let me explain that the proof of this depends on plumbing constructions. On a plumbing construction. Which generalizes the idea of a generalizing or extending, if you like. Well, there are various plumbing constructions for extending what is known for curves. So where does this come into it? Let's assume that Q is at least 2. I can reduce to this case by making a branch covering of, pulling back by a general branch covering of the base. So we know that the tangent bundle, the tangent space, excuse me, at the stack is naturally a sum of lines, one for each point on Z. And then, and this maps to the tangent space, the stack of curves, which is, of course, just H1 of C. Now, for any point A, we have the following construction. So I have 0, CC, CC twisted by A, and then I get another line L prime A to 0. So this gives, if I take cohomology, L prime A sits inside H1 of C with coefficients in TC. And the whole point is that LA maps to LA prime. And LA prime is represented by a Schiffer variation of C. So in other words, so deformations of X along the line LA along in the LA direction map to Schiffer variations of C. So what are these Schiffer variations? Well, if we go back to the the construction here, what is this? So this this line is given by a what this is doing is this is simply introducing the variation. So L prime A is, whoops, let's replace a local coordinate Z by Z plus T over Z. All right, so we make a meromorphic variation, the simplest possible meromorphic variation. Or let me express this as a slogan. You delete a Z disk from C, and then glue in a new disk. A new disk with coordinate W, which is Z plus T over Z. So what I want to do is actually to explain this in a way which makes it possible to see how to make calculations. So let me expand the slogan. So we fix our curve C. We have a point A in C and a coordinate Z on C at A. And fix delta, a positive real number delta, such that the disk where Z is the absolute value of Z is at most is less than delta is actually in C. In other words, this disk does not overlap itself. And then take delta sub T with the disk the absolute value of T is less than delta squared. And then inside C cos delta T, we take the complement U of the closed set where absolute value of C squared is less than or equal to the absolute value of T. And let's say, for convenience, we'll take G to be then this open set U intersect the locus where the absolute value of Z is less than delta. Right. So the idea is, so U is almost all of this product here, except I've deleted some parabolic region defined by this inequality. And then in the complex plane with coordinates Z and W, we'll consider the region F defined by the inequalities that W minus Z and Z Both have absolute value at most delta. So then F has an involution iota such that iota upper star of Z is Z minus W. W is invariant. So if T, so iota upper star T is T, where T is Z into W minus Z. And remember that, so W equals Z plus T over Z. And then go back to then G. I can map G to the geometric quotient of F by iota. This is one-to-one and étale onto its image. So it's an open embedding. So what we can do, so what we get is we get G sitting inside this chart F modulo iota, and it also sits inside U, which is, remember, open inside C cross. So U was almost all of C cross delta. And then we define our variation to be the union of these two charts. And it maps down to the T-disk. And this is our variation. So the point is that we can now calculate, for example, periods. Well, suppose that omega j, depending on t, is a basis of the space of one forms on C sub t. Maybe normalized. The integral around an A cycle of omega j. It's Kronecker delta. So then we can write. Then there are holomorphic two forms, capital omega, on the total space. This, remember, this is the total space of the variation. This is two-dimensional, such that omega j is the residue along the curve CT of omega j divided by the equation defining C. Defining C sub t. So the idea is that to make a calculation, we can now pull back to F and expand. And expand. So just think, using the method of undetermined coefficients, I will use this is simply F to the M, W to the N, dz wedge dw. And note that F maps down to the T-disk also, but this map is not smooth. But we pull back to F, so but then omega j is then still the residue of omega j divided by z squared minus wz plus t. And this is m1t, so this is omega j evaluated at the point A plus t times eta j. J is modulo t squared. And you simply expand this, and you expand, well, you compare coefficients. And you find that omega j evaluated at A, evaluated at A, there's no subscript there, is equal to B10 plus B01 plus OZ dz. Let me write it down here. Plus OZ dz. Whereas the derivative is then B01 z to the minus 2 plus O1 dz. So it's of the second kind. But then, but we don't really, we're not in a position to compare the coefficients yet, because at the moment we don't have any further constraint on these things. But then iota invariance gives B01, B10 is equal to minus B01. So this derivative is minus z squared times omega j evaluated today plus O of 1 sorry, that makes sense, plus O of 1 easy. So in terms of the derivative, this is going to go from F1 to F0 modulo F1. We're on a curve now, not a surface. So then the derivative is, we see that its kernel is H1 C omega 1C, the one forms which vanish at A, and its image is the line, well, the cohomology class generated by the line of the form eta A of the second kind. Now, for elliptic surfaces, the line LP is then obtained with for elliptic surfaces, I should say the line LP, line LA, is then obtained, will then integrates to a variation which lies over a Schiffer variation of C. C. And then instead of, we can calculate with differentials in the same way, that we can still calculate using, calculate n+1 forms in, well, n+1 forms instead of n forms. But the calculation is much the same. But since omega-2 of x, or let's say omega-3 of x, so this picture here, so I've got a capital F, since omega-3 is the pullback of a line bundle on C, we have omega J 3 forms X, 3 forms omega J on X, and omega J is exactly the same as in the curve case. C to the n, W, T to the n, W to the n, dz wedge dw. So there's a fiber coordinate, where r is a fiber coordinate, which does not enter into the calculation at all. So this, if we chase through the calculation, so simply then making exactly the same calculation as the Schiffer variations, calculate as for Schiffer variations, and the theorem drops out. Okay, well, I've come to the end of the time. I don't have time to explain to you how this is leads on to a discussion of Torelli-related issues for these surfaces, and I don't have time to carry on and talk about generalizations and variations on this theme, variations on a variation, if you like. So I'll simply stop there, and thank you for your attention.
Thank you. I think we have maybe, or at least I have some time for questions. If someone wants to ask questions.
Of course.
Or make comments. No? Well, then maybe being mindful that it's, what is it, 11 GMT. Maybe we can leave it here. Thank you very much, Nick. The goal for this seminar is to continue beyond September, but probably in a slightly different format. Is something we have to kind of decide. So if you have any suggestions or you want to be involved in some way, please send me an email, and I'll be very, very happy to read them. Thank you, Nick, and thank you everyone who came. Bye bye.
Okay, bye bye.